So we consider the same standard classical linear regression model, and we are going to test this equality. So the difference from the standard, like simpler restriction is that it involves two parameters. So that's a small difference. Let's see. So the unrestricted model is just OLS, right? There is no special thing here. All the regressors are exogenous, and you may consider GMM, you may consider OLS, or you may consider GMM. And we know their equivalence from chapter 4, so I'm not going to go in detail. So your unrestricted estimator will be written in this way, like beta hat 1, beta hat 2, beta hat k. So unrestricted estimator has k-dimensional estimates. By the way, I did not include this in the question, but restricted model. Let's think about it. So we are going to include beta 1 equals to beta 2 as a restriction. Then what does it do? So I'm going to write it this way. So we have k regressors and k coefficients, but the second parameter equals the first parameter. Okay, so you may write it this way. Okay, so the difference here is I change it beta 2 into beta 1. So that is also same as the first coefficient. That means x1 and x2 has the same coefficient, so we can factor out beta 1. And everything else being the same, there is no change for the other variables. So then you have to count these two, the sum, as one regressor, right? So there are k minus 2 regressors plus 1 regressor. So that means it is a new regression model where your restricted regressor vector can be written as x1 plus x2 for the first element, and then x3, and then x4, and then xk. Okay, so in the original unrestricted vector, x is k by 1 vector, the regressor vector x was k, but in the restricted model, you have to reduce one parameter. So the number of parameters, number of coefficients is k minus 1. So then something has to change. That's here, right? So this is the difference, and you are going to reduce the number of parameters by just treating two regressors as one by adding them. Okay, so that is the restricted estimator. But I'm not going to use the restricted estimator in this question. It is just I should have updated the question, but I didn't. Okay, now then let's design our test, right? So we are going to reject H0 based on wild test idea if beta 1 had unrestricted estimator minus beta 2 had unrestricted estimator, the difference is too large. Okay, so pretty intuitive. So I believe their two parameters are the same. So then their estimated difference should be close to 0, right? But if they are too large, too different from 0, I'm going to reject the null hypothesis. So too large means mathematically we are going to reject if the absolute value of the difference is greater than something, c, right? Then how can now then the problem is to find such critical value c. We have to find the c. You can calculate this much. This can be calculated, so you just need to find out the critical value. The required condition is this is alpha under H0, right? So if the null hypothesis is correct, then the rejection, this is the rejection probability is alpha, right? So for example, 5%, 1 minus significance level. So you allow alpha percent type 1 error. So this is type 1 error because if you reject the null hypothesis when it is true, that is type 1 error. So we are going to do that. So then what we need to do here is we need to find the distribution under H0. So we need null distribution of this guy. Okay, then everything else is just standardization. How we do that? We know in general, unrestricted estimator is just on OLS. Okay, so then it is straightforward, right? We know the unrestricted OLS can be written as the variance can be written as this way. We know the sandwich formula. You can use the GMM theorem or the OLS result. I believe it is straightforward. I'm not going to prove that. So we are going to do this. And what I'm going to do here is I will represent the restriction as a linear form. Okay, so the difference here is beta is k by 1 and R is a matrix q by k. Beta is k by 1, R is q by k, so 0 is q by 1 0 vector. Okay, and then what is, so that means I want R times beta 0 equals beta 1 0 minus beta 2 0, right? How can you do that? Your matrix must be 1 and minus 1 and 0 0 0 0 0 0. Of course, there are k minus 2 zeros. So then if you multiply this matrix to beta, k-dimensional vector, then you are going to get the difference between the first two coefficients. That is pretty straightforward. Okay, then of course q is 1 and rank of R is also 1. That is obvious. Right, okay. Then, based on the OLS asymptotics, I'm going to multiply R to the asymptotic result. Then we have another straightforward normal distribution. Okay, so by the continuous mapping theorem, you will get this new variance. By the way, that is the new variance. I'm going to write that as a sigma squared is R times V times R transpose, right? And you can see that it is variance of beta 1 minus beta 2, obviously. And then obviously it is variance of beta 1 hat plus variance of beta 2 hat minus 2 times covariance of them, right? Beta 1 hat and beta 2 hat. So it is just an elegant way to calculate the variance form, right? Anyhow, I'm going to write that as sigma squared. And here, now let's think about what happens if, so we are going to calculate this guy, right? But this, but the other part is unknown, right? So we will study what happens if H0 is correct. Then R times beta 0 is 0 in our hypothesis. So square root to n times R times beta hat U converges to normal distribution 0 sigma squared. So it is simple. But let's think about it. If H0 is wrong, then what you can calculate, R times beta hat U equals, this is what you calculate. You have to decompose your calculation into R times beta 0 plus square root n times R plus beta 0, R times beta 0, right? So this converges to normal distribution, but this guy, so let's say R beta 0 is delta. then this guy converges to is not converging. It is going to just square root 10 times delta. Then this part does not matter because it is just stable normal distribution, but this guy is going to plus or minus infinity. So it's going to plus infinity if delta is plus, and if delta is negative, it's going to negative infinity. So then this justifies our test statistic. Okay, and also we learned our null distribution. Using the null distribution, I'm going to define the test statistic in this way. So beta 1 hat minus beta 2 hat divided by sigma hat over square root n, right? It's common t-test, right? And this sigma hat, so the only problem here is sigma hat. If sigma hat converges to sigma correctly, sigma squared converges to sigma squared, then this will converge to normal distribution 0, 1, standard normal distribution. Okay, then you can choose reject the null hypothesis if the test statistic is the absolute value is greater than C, where C is normal distribution alpha over 2, right? So in the normal distribution, you have to use minus C and C, so that this probability is alpha over 2, this probability is alpha over 2, and in the middle probability is 1 minus alpha. So you have seen this many times. And then the only remaining question is, how can you calculate sigma hat, right? So, and we have to guarantee sigma hat is consistent. That's also easy. Remember, sigma squared is r times v times r squared, r transpose. Okay, we are going to define r hat as sample average of x transpose inverse, sample average of u hat squared x transpose, and sample average of x transpose inverse. Okay, so then how can we define u hat? The residual is yi minus xi transpose beta unrestricted. Okay, everything is so straightforward. So this variance calculation is the same as OLS variance calculation. That means your sigma hat will be r times v hat times r transpose. R is a known matrix, like with 1 and minus 1 and zeros. So that is calculatable, and v can be calculatable, and r transpose, of course, known. And then, of course, sigma hat will be square root of sigma hat squared. So it's square root of rv hat times r transpose. So this is how you define a t-test, right, based on normal distribution. But also you may use the chi-square distribution, right? Because square root 10 times beta hat 1 minus beta hat 2 unrestricted follows normal distribution 0 and sigma squared, then it is easy to see that square root 10 times beta hat 1 minus beta hat 2 transpose sigma squared inverse times square root 10 times beta hat u1 minus beta hat u2 follows chi-square rank of the variance. And of course, it is scalar, right? So you can simplify n times beta hat u1 minus beta hat u2 squared over sigma squared converges to chi-square 1. Of course, what you calculate is square root, sigma hat, right? Instead of sigma, you have to utilize sigma hat because sigma is unknown. Then still you get the same result, and the critical value is, so you have to choose a critical value such that this probability area is alpha, and this is 1 minus alpha. So C should be, critical value C is 1 minus alpha quantile of chi-square 1. So that's how you find the critical value.